Okay, so we are talking about asymptotic notation. So we have the big theta notation. So we define the big theta of f of n as, this is the mathematical definition of big theta. So it is basically set of all function gn such that, so gn is bounded both sides by fn for all n greater than some n0. Okay, so this is the mathematical definition of it. So for example, if we take the big theta of n square, this is basically set of all function which should be bounded by n square by both sides. So this is C of n square for all n greater than, where C1 C2 are two constant. So for example, we have taken, so if our time complexity is Tn, say 5n square minus 10n plus 2. Okay. So for this we can see that we can choose some constant suitably C1 C2 for some after some n. So such that we can always, so this is bounded by both C1 n square less than equal to this less than equal to C2 n square. We can always choose C1 C2 some suitably some large constant, or so then this is basically belongs to big theta of n square, but we will just write this is big theta of n square. Okay. And in engineering sense what we have mentioned, so we just ignore the all lower order term, because higher order term is n square, we will ignore all lower order term, then we ignore the leasing coefficient. So this is basically n square, so that is big theta of n square. Okay. But we do have a mathematical definition. Now we talk about big O. So what do you mean by big O of n square or big O of n cube, big O of any functions? So big O is basically bounded above. So big O of Fn is basically set of all function Gn such that Gn will be less than some C into Fn. Okay, and this is true for all n greater than or equal to C0, and where C is a positive constant. Positive constant. Okay, so basically it is a upper bound. So if we have such a upper bound, then say for example big O of n square basically set of all function such that it is bounded above by n square. Okay. So if we can choose a C such that positive C such that it is less than this, so any function like this, say 10n square plus 5n plus 2, like this. So or maybe say minus 5n, like this. Now if we choose C to be, for this example, if we choose C to be greater than 10, then this can be shown as less than Cn square. So that means this is basically big O of n square. Okay. So this is the big O notation, this is the upper bound. So if our time complexity is this, then this is basically big O of n square. Now we do have another notation, this is called big omega. So big omega of Fn, which is basically the lower bound, which is basically set of all function Gn such that Gn is greater than some C of Fn, and this is true for all n greater than or equal to n0. This is the mathematical definition, where C is a constant, this C is a constant, C is a positive constant, as you know. So big omega of n square, for example, is set of all function which is bounded below by n square, some Cn square. Okay. So basically big theta is basically what? Big theta is basically big theta of say n square or any other function is basically set of all function such that it is bounded both sides by this function, say any function f n, C of f n less than equal to g n less than equal to C 2 of f n. Okay. Now, this is big theta. Now, if we have, so this, if we have this is big O of f n, and if we have this only, this is big omega of f n. So, if we have big theta means both big O and big omega. So, if T n is a big theta of say some f n, this implies T n is both big O of f n and big omega of f n. So, big theta is basically both side bounded, and this big O is basically upper bound and this is the lower bound. So, we usually go for upper bound, because if we say that our time complexity is greater than 5 seconds, for example, then that does not make any sense. Greater than 5 seconds does not mean that it will be less than something, but if we say our time complexity is less than 10 seconds, something like that, or less than some n square. So, that has some sense. So, usually we go for the upper bound, I mean the big O of big theta of big O of n square. Okay. So, these are the asymptotic notation we will use for our time complexity, because this is to help us to get rid of from the machine dependencies. So, now with the help of this asymptotic notation, we will analyze the insertion sort worst case. We will analyze the insertion sort, all the cases using this asymptotic notation. Okay. So, let us analyze the insertion sort, time complexity basically, analysis of insertion sort. So, basically the time complexity. So, run time complexity means run time, and there is another one, the space complexity. So, insertion sort space complexity means in insertion sort we are using we have given array, and we are not taking any extra array for that. So, it is a in place sort. So, insertion sort is a in place sort, in place sorting algorithm. That means it is sorting in the array itself. We are not taking help of any extra array to sort it, to run the code. We are just taking one key. So, that is not compared to n. So, just one key we are taking some variable like I j. So, that is one or two variables. So, that order is theta of 1 size. So, that is why it is called in place sort. That means, we are not taking any extra memory for running this code. So, we are sorting everything inside the array, whatever array we have, we are managing there. So, this is not taking any extra memory to run. So, now that is the space complexity. Now, we talk about time complexity. So, first, we know that we do 3 types of analysis. So, first one is worst case analysis for insertion sort. Okay. So, what is the worst case analysis for insertion sort? For insertion sort, worst case is if the input is reverse sorted. So, for insertion sort worst case, input is reverse sorted. For example, if we have say input like 9 reverse sorted 6, 5, 3, 2, 1, if this is our input. Okay. Now, if you run this insertion sort on this input, so we start with j is equal to this. So, we compare this. So, j has to 6 has to come here, 9, 5, 3, 2, 1. Now, j is pointing here. So, then 5 has to come here. So, 5, 6, 9, 3, 2, 1. So, j is this. Now, 3 has to come here. So, 3, 5, 6, 9, 2, 1. So, j is this. Now, 2 has to come here. So, 2, 3, 5, 6, 9, 1. Now, 1 has to come here. So, finally, we got 1, 2, 3, 5, 6, 9. So, for insertions, this is the execution of the insertion sort for a reverse sorted input. So, for everybody has to come forward to the beginning. Okay. So, that is the worst case. So, that is why it is taking maximum time. So, now we want to analyze this. So, if we have this for loop, we know this is we have a for loop. So, what is the time complexity? So, time complexity is basically summation of the. So, let us just so if we just write the insertion sort code again, it is basically for j is equal to 2 to n, key is equal to aj, I is equal to j minus 1, and then we have a while loop while I is greater than 0 and key is less than ai. Then only we run this, then ai plus 1 is ai, and then I is equal to I minus 1. So, this is 1, 2, 3, 4, 5, 6 and 7 is after this while loop ai plus 1 equal to key. So, this is the code for the insertion sort. Now, to find the time complexity of it, so we have a for loop. So, this is starting from j is equal to 2 to n. Now, here we are doing something. So, this is the assignment we are doing. So, this is the worst case. So, this is the assignment we are doing. So, this is taking theta 1 time. Again, we do not care about how much time our process, how much time our hardware is taking. Okay. So, this is also theta 1, and here this 2 is also taking theta 1 time, because here we are just assigning something. Again, this is theta 1, this is theta 1, but size of this loop is order of j for a given j. So, if we fix a j, suppose this is our j, this is our j and this is our key. Now, this key is comparing with this, this key is coming long way to the beginning, and every time we are spending constant effort, because that is come under theta 1, but if we are machine dependent, then it will take some different machine will take different time, but we do not bother about that. So, we will just think that this is taking some constant time, some c. Okay. This is not related to n. So, that is why it is basically theta of j, because j times theta of 1. So, for each, if we fix a j, since j has to come long way to the beginning. So, every time it is comparing and doing something. So, those whole thing it is just the theta of 1, and then so this is basically theta of j. Now, this is basically a arithmetic series like 1 plus 2 plus 3 plus up to n. So, this is basically n into n plus 1 by 2. So, this is theta of n square. So, this will give us theta of n square. Okay. So, this is the worst case runtime for insertion sort. Worst case runtime for insertion sort. This is in asymptotic sense, asymptotic notation, because we do not want the exact one, because exact one is a headache, because it will be machine dependent things. So, we do not care how much time exactly we are spending here, how much time we are spending this I greater than 0 checking, how much time our machine is taking. So, we just take this as a constant time theta of 1. Okay. So, that way it is the asymptotic analysis. So, this is the worst case runtime for insertion sort. So, now we want to do best case, best case analysis for insertion sort. So, what is the best case? So, this is the second, so best case analysis for insertion sort. So, when is the best case? If the input is already sorted. This is the best case for insertion sort if the input is already sorted. Okay. So, if the input is already sorted means what? If it is say for example, say if the input is 4, 3, 4, 6, 7, 9, 10, 11. Suppose this is our input. Okay. Suppose this is our input. Now, if we want to run our insertion sort on this input, so on this piece of code, so we start with j is equal to 2, then for that I is pointing here. So, we compare this is greater than. So, we are not entering into this. So, this will stop here. So, but we are doing some comparison over here. So, it is not entering here, but this will taking some time, this check and this check, at least we are doing this check. So, this is, but again this is a constant time we are spending. So, that is also theta 1. So, this is the I and this is j is pointing. So, we are not doing anything, now j is pointing here. So, just a one comparison we are doing. So, theta 1 time we are spending for this. So, again nothing, j is pointing here, j is pointing here, nothing, j is pointing here, I is pointing here, nothing, then j is gone. So, basically time is basically Tn is basically summation of j is equal to 2 to n, and every time we are just doing the one comparison, I mean just to check whether this key is, and that will take theta of 1 time, machine independent, I mean asymptotic sense. Okay. So, this is basically theta of 1. So, this is the best case runtime for insertion sort, best case runtime. This is linear, but this is only occur if the input is sorted. Best case runtime for insertion sort algorithm. So, this is occurring only if the input is sorted, not for any other input. So, this is the only linear time algorithm, linear time, but this is a very special case when the input is already sorted. So, but the worst case is n square. Okay. So, now we talk about another analysis which is called average case analysis. So, this is the best case which is big theta, basically this is big O and big omega also. So, now we talk about the third one which is the average case analysis of the insertion sort. Okay. So, average case, when we do the average case analysis for any algorithm, then we must have a something called some randomized algorithm. That means, we must choose the input, some randomization will be there. We will talk about this in more details when we will talk about randomized quick sort. So, anyway, so this is, but here intuitively we can just think that so worst case, this is a j loop. So, this is basically summation of, we have a outer loop, j is starting from 2 to n. So, in the worst case, j is coming all the way to the beginning and we are inserting the key, and in the best case j is just comparing 1. So, in the average case we can say j is coming halfway. So, this will be theta of j by 2, but this is the intuitive analysis, it is not exact average case analysis one should do, because for that we need to take the distribution of the input pattern, then we must talk about expected value of T n. But this is roughly intuitively we can say like that, the j is coming halfway to the beginning. So, this is again will be, because this is arithmetic series, just half will take common, this is again theta of n square. big theta of n square. So, that means this is big O and big omega of n square. So, this is basically average case runtime for insertion sort. Okay. So, now we have seen insertion sort, which is having the best case is linear, which is theta of 1, but that is for best case, that is for particular input, it is not guaranteed for any other input, this is the minimum time. Average case is also n square and the worst case is n square. Okay. So, now we talk about a algorithm, sorting algorithm, where worst case is better than n square. So, that is called merge sort. Okay, so how much time we have? Okay. Okay, so in merge sort, this is also another sorting algorithm. So, we have given an array of size n. So, the idea is this is a type of technique which is called divide and conquer technique. So, we have a problem of size n, we divide the problem into sub problems of lesser size and then we solve the sub problem recursively, that is the conquer step, and then we combine the solution of the sub problems to get a solution of the whole problem, that is the combined step. We will talk about in more details divide and conquer technique, but this is the one example of such a technique. So, basically we have a array of size n. What we are doing? We are just dividing the array into two parts, n by 2, n by 2, provided n is even or not. If n is not even, we must put a lower ceiling or upper ceiling. Okay. Anyway, you can be floppy little bit here. Now, so we have this subarray, this subarray. Now, we sort this subarray, we sort this subarray recursively by calling the same function merge sort. And then once we got the solution of this subarray, once this is sorted, once this is sorted, then we call a combined step, that is called merge subroutine. We call a function merge, which will take this two sorted array and give us the full sorted array. So, that is called merge. So, let us write the code. So, obviously, if n is equal to 1, we are done, we return, else what we are doing, we just recursively sort two subarrays recursively by calling the same function. One subarray is a 1 to n by 2 and a n by 2 plus 1 to n. But to be very precise, we must put a ceiling over here, because this may not be always integer. But we were doing asymptotic analysis. So, this is okay. So, this is we just sort this subarray, we are dividing the array into two parts, we sort this subarray, we sort this subarray, then once we have the solution of these two subarray, we call the what is called merge subroutine. Okay. So, this is the code for merge sort, this is the recursive calling. So, we call again to sort this, we call again the merge. So, again it will divide into two subarrays, sub subarray. So, again it will divide sub subarray. So, this way we will go down until we reach to the n is equal to 1. Once we reach to the n equal to 1, we merge this. So, the merge call will be log n, the height of the tree, like this. Anyway, so now we talk about this merge. What is the merge subroutine? So, merge, what it is taking? What it is doing? It is taking the two subarray, two sorted subarray, and it is giving on the whole array. So, for example, suppose we have two sorted array, say 9, 6, 4, 3, 1, and another thing say 10, 8, 7, 5, and say 2 sorted array, and they may not be equal. Okay. And so, this is a sorted array, this is a sorted subarray. Now, we call merge. So, for merge, what we take? We point the least element of each of these arrays. So, least element will be this element. Now, we compare this to list. Now, whichever is the least among this, we will return it. So, we will return 1 and we point to the next least element of the array. Now, we compare these two. So, 2 is the least, we output 2. So, 3 is the least, we output 3, 4, 5, 6, 5 is the least, we point this, 6 is the least, 9, so 7 is the least, 8, so 8 is the least, so this is 7, 8, and then 10, so 9, 10, 9 is the least, and then 10. So, this is the Mart subroutine. Okay. So, this is the Mart subroutine. So, basically we have two sorted array, and this March is taking the input of these two sorted array and giving us the whole array. So, we will talk about the time complexity and the space complexity of this algorithm in the next class. Thank you.